Hello, welcome back to Digital Urim. In the first part, we learned the foundation of Linux permissions. We saw what RWX means. We learned that R means read, W means write, and X means execute for files. We also learned that, in directories, X has a special meaning. It allows a user to enter or traverse a directory path. We learned how to read a permission string like dash rwx r-x r-dash. And we clarified something very important. The first character is not a permission. It represents the file type. After that first character, we see the permissions for the owner, the group, and others. We also learned octal notation. We saw that R is worth 4, W is worth 2, and X is worth 1. That is why RWX equals 7. And that is why permissions like 755, 644, or 777 are not random numbers. Each number represents a security decision. Now we continue with the most important part. What happens when those permissions are misconfigured? Because understanding permissions is not just a Linux administration skill, it is a cybersecurity skill. Permissions define who can read information, who can modify files, who can execute code, and who can change the behavior of a system. And when permissions are too open, risk increases. A misconfigured permission may look like a small detail, but in cybersecurity, small details can become attack paths. Think about the permission 777. As we saw in the first part, 777 means that the owner, the group, and others can read, write, and execute. In other words, everyone can read, everyone can modify, everyone can execute. Sometimes someone uses chmod 777 because a file is not working, because a script fails, or because an application cannot access a folder. From a convenience perspective, it may look like a quick solution, but from a security perspective, it can become a serious problem. Because you are not only allowing the system to work, you are also allowing any user on that system to modify or execute that resource. And if an attacker gains access as a standard user, that excessive permission can become an opportunity. This is where an important concept appears: misconfiguration. A misconfiguration is a security weakness created by an incorrect setup. Many attacks do not begin because the attacker has an extremely advanced tool. Sometimes they begin because something was configured incorrectly. A private file was left readable. A script that should have been protected was left writable. A directory that should have been restricted was left open. An executable used by an important process can be replaced by another file. And when that happens, the attacker does not need to break the front door. They only need to find the door that someone left open. Now let's imagine a realistic scenario. A company has a server. On that server, there is an automatic backup script. That script runs every night. Its job is to copy important files to a safe location. So far, everything looks normal. But there is a problem. That script runs with elevated privileges. For example, it may run as an administrator, root, or as a service account with access to sensitive information. Now imagine that the script file has permissions that are too open. For example, any user can write to it. That means a standard user can modify the content of the script. Now an attacker gains access to the system. The attacker is not an administrator. The attacker is not root. They do not have full control. They only have limited access. But the attacker starts observing the system. They look for files. They look for directories. They look for scripts. They look for scheduled tasks. They look for files that are executed with higher privileges. And then they find the backup script. The attacker checks its permissions and discovers something critical. They can modify it. At that moment, the attacker has an opportunity. They do not need to become administrator directly. They only need to change the content of the script. They can insert a malicious instruction. They can add a command that creates a new account. They can copy sensitive data. They can open a connection to another system. They can run an action that would normally not be allowed for a limited user. Then they wait. When the scheduled time arrives, the system runs the backup script automatically. But it does not run as the attacker. It runs with the elevated privileges of the backup process. And this is where privilege escalation happens. The attacker started as a standard user, but they managed to make their code run with higher privileges. That is a form of privilege escalation caused by misconfigured permissions. This example is important because it shows something real. Privilege escalation does not always depend on a complex software vulnerability. Sometimes it depends on a bad configuration, a writable file, an unprotected service, an insecure scheduled task, a folder with excessive permissions, or a poorly configured access control list. And this principle applies to both Linux and Windows. In Linux, we may find risks in scripts, binaries, shared directories, cron jobs, services, or files with permissions that are too open. In Windows, we may find risks in services, folders, scheduled tasks, modifiable executables, or poorly configured NTFS permissions. The principle is the same. If something runs with high privileges but can be modified by a low-privileged user, you may have a potential privilege escalation path. Now let's briefly look at Windows. Windows does not use the basic RWX model used in Linux. Windows uses a more granular model called ACL, or Access Control List. If you select a file in Windows 11, right-click it, open Properties, and go to the Security tab, you can see which users or groups have access to that file. There you may see permissions such as read, write, modify, full control. And here there is an important technical difference. Write is not the same as modify. The write permission may allow a user to create or add content, but modify allows the user to change and delete files. And full control goes even further. It can allow the user to manage permissions, change ownership, and fully control the resource. This makes Windows more detailed than the basic RWX model. But the security question remains the same. Who can do what? Who can read? Who can modify? Who can execute? Who can delete? Who can take control? In cybersecurity, that question is fundamental, because an attacker always looks for actions that allow them to move forward. If they cannot access one file, they look for another path. If they cannot execute code directly, they look for something that can execute code for them. If they cannot modify a service, they look for a folder where they can write. If they cannot become administrator directly, they look for something that the administrator runs for them. That mindset is extremely important. A beginner looks at permissions and thinks, this is just configuration. An analyst looks at permissions and thinks, this defines risk. Now let's talk about a common mistake. Many times when something does not work, someone changes permissions too broadly. For example, chmod 777 file.sh, or they open access to a folder so an application stops failing. That may solve the immediate problem, but it can create a much bigger security problem. Because if everyone can modify a file, an attacker can modify it too. If everyone can execute a file, an attacker can execute it too. And if that file is part of an automatic or privileged process, the risk becomes much higher. Security is not about allowing everything to avoid errors. Security is about allowing only what is necessary. This is known as the principle of least privilege. The principle of least privilege says that a user, process, or service should have only the permissions required to perform its function, no more, no less. If a user only needs to read a file, they should not be able to modify it. If a process only needs to write logs, it should not have full control over the system. If a script should only be executed by an administrator, it should not be writable by every user. This principle is one of the foundations of defensive security. Now think like an analyst. When you review a system, you should not only ask what files exist, you should ask who can read them, who can modify them, who can execute them, with what privileges do they run? Are they part of an automatic task? Are they used by a service? Do they belong to a critical path? Can they be changed by standard users? These questions help detect risk before it becomes an incident, because a poorly protected file can be more dangerous than it looks. It can become an entry point, it can become persistence, it can become code execution, or it can become a path to elevated privileges. Now let's connect everything. In the previous video, we talked about users and privileges. In the first part of this video, we learned how permissions are read, and now we understand why those permissions matter. Because if an attacker compromises a limited user, they still have restrictions. But if they find misconfigured permissions, they may try to escape those restrictions. They may look for writable files. They may look for scripts executed automatically. They may look for scheduled tasks. They may look for misconfigured services. They may look for paths where they can write and that are later used by privileged processes. That is what can turn limited access into a possible privilege escalation. And that is why this topic is so important for cybersecurity. You are not learning RWX just to manage files. You are learning to read the system like an analyst. You are learning to see where risk may exist. You are learning to detect which permissions could allow movement, persistence, or escalation. Today, you learned that dangerous permissions can become a real attack path. You learned that chmod 777 may be convenient, but it can also be risky. You learned that a misconfiguration can allow a limited user to modify something that later runs with higher privileges. You learned that Windows uses ACLs, a more granular access control model where permissions like write, modify, and full control have important differences. And you learned that the key question for an analyst is not only, does this file exist? The correct question is, who can do what with this file? In the next video, we will move into an even more interesting topic: SUID, SGID, and sticky bit. These are special Linux permissions, and they are important because they can allow a program to run with privileges different from the user who launched it. When they are configured correctly, they serve legitimate purposes. But when they are configured incorrectly, they can become very interesting paths for privilege escalation. That is the next step. Understand, defend, grow.